Hello and welcome to our video. For today, we're going to explain the quantitative analysis of ethanol in local alcoholic beverages using GC-FID. So first of all, we're going to start with the introduction on the local beverages itself.
Alcohol has a local identity that is a key component of the societies of two states, Sabah and Sarawak in East Malaysia and the island of Borneo. Combining information obtained from previous studies and questionnaire survey, it concluded that indigenous population of these regions use homemade rice wine known as tuak patapai and consumed mainly during harvest festival and social events. They are both very strong wines made from fermented rice, and this is a paramount local delicacy, especially during festivities such as harvest time. In fact, to decline these drinks is contrary to manner and ethical requirements, although such beverages play their part as an integral component of the culture. The quantifications of ethanol in alcoholic beverages is crucial for regulatory compliance, quality control, and consumer safety. Gas chromatography coupled with flame ionization detector, which is GC-FID, is a reliable and widely used analytical technique for this purpose. This method offers high sensitivity, specificity, and the capability to analyze complex mixtures.
So you already learned a little bit about our local alcoholic beverages in Borneo. Next, Ethan will be explained on the principle of the GC-FID and more details about the flame ionization detector, which is FID.
Gas chromatography is a separation technique where the sample is vaporized and carried by an inert gas to mobile phase through a column packed with a stationary phase, allowing the different components of the sample to travel at different rates and separate. The flame ionization detector FID is a detector used in GC that measures ionizable component in the sample as the eluted compounds from the GC column are burnt in a hydrogen flame. They produce ion, and the resulting ion current is proportional to the amount of the compound, which is then recorded as a chromatographic peak. The flame ionization detector FID operates by vaporizing the sample in a hydrogen H2 or air flame, breaking down organic molecules into ions through combustion and collecting this ion on a bias electrode to measure as a current. This detector is cost-effective, requires minimal maintenance, and can withstand harsh laboratory conditions, making it suitable for gas chromatography analysis. It is particularly effective for detecting hydrocarbon and other organic compounds, but has limitations such as inability to detect inorganic substance, limited detection of certain highly oxygenated or functionalized species, and sample destruction as it oxidizes an all oxidizable compound. The flame ionization detector FID is the most widely used detector in gas chromatography due to its reliability, versatility, and ease of use. It operates by detecting the ions produced when organic molecules burn in hydrogen flame, which are proportional to the amount of carbon in the sample. The FID is sensitive to most carbon-containing compounds, with a linear range of 7 orders of magnitude and a detection limit in the picogram range. It is commonly used in environmental analysis, the petrochemical industry, and internal combustion engine emission measurement, and is particularly effective for detecting hydrocarbon and other organic compounds.
So we're done with the GC-FID. Moving on, we have methodology. In this, Ethan going to explain the sample preparation and the importance of it, and he also be explaining the instrumental analysis. While the data analysis, I'm going to explain it later on after Ethan on how to determine the concentration in the alcohol by using the calibration curve.
To quantify ethanol in a local alcoholic beverages from Sabah and Sarawak, samples are collected and diluted with a suitable solvent. Using gas chromatography with flame ionization detection, the diluted samples are analyzed by separating their components. The FID burn the eluted components, producing ion for detection. Ethanol and the other volatile compounds are quantified using standard references and calibration curves. Data analysis determines ethanol concentration and profiles, compares regional variations, and interprets findings in the context of traditional production methods and cultural significance. Sample preparation is a crucial step in a gas chromatography analysis, as it extracts, purifies, and concentrates the target analytes. For a liquid example, dilute the sample in a low boiling solvent to bring the analyte concentration within the GC-FID analytical range. For solid samples, dissolve or extract the solid in a low boiling solvent with a filter the solution before GC analysis. Vapor samples can be injected directly but may require some sample preparation to remove non-volatile components. Proper sample preparation ensures accurate result, high sensitivity, and minimize the risk of damage to the GC system.
So, before we moving forward to the calibration curve, we need to understand the Beer's law in the GC-FID. So, Beer's law is a linear relationship that relates to absorption of light by a substance to its concentration in a solution. So, its formula is A, the absorbance, epsilon is the molar absorptivity, B is the length of the light path, and C is a concentration. So, the principle of using the linear relationship between concentration and detector response will also be applied in GC-FID for quantitative analysis. In this context, we establish a calibration curve correlating ethanol concentration to the GC-FID response. So, next is the calibration curve. So, in order for us to find the calibration curve, we need to prepare a standard solution of the ethanol. For example, solution can be 0.1, 0.5, 1%, 2%, etc. So next, the solution will be injected into the GC-FID system and the fixed area will be recorded. So same goes with our sample, which is the alcoholic beverages. So this is important because we want to compare the result from the sample with known concentration in order to determine the concentration of substance in the sample. So moving on with the calibration curve, this is the example of calibration curve that we got. So this is the alcoholic beverages analysis on palm wine from Sri Lanka. So by examining each of the 5 standard calibration solution and charting the ethanol level against the corresponding fixed area, an external standard calibration was carried out. The linear regression calibration function is displayed in the graph. Excellent linearity for this approach was demonstrated by the correlation coefficient for this calibration, which was 0.999. Because of this, the linear range for this approach is 1 to 5%. The intercept standard deviation and standard error are 0.058 and 0.62% respectively. So next is the result and discussion. So here we got the peaks of retention time for ethanol standard solution. So for the ethanol standard solution was 9.63 minutes. The peak of the palm wines, which is the Palmyra, Toddy, and Arak sample, was detected at 9.63 minutes and 9.71, which were the confirmed presence of ethanol standards. Deviation of the calibration graph is 0.058%. So the recovery of the ethanol standard was in range of 98.453 to 101.833%.
Gas chromatography is widely used analytical technique for quality control in various industries, including food processing, pharmaceutical, and automotive manufacturing. It helps ensure the purity and consistency of product by detecting quantifying specific compound. GC is used to monitor the ethanol content in beverages, ensuring compliance with regulatory requirements, maintaining consumer safety. Additionally, GC is used in environmental monitoring to detect and quantify pollutant in air, water, and soil samples, helping researchers understand the impact of pollutants on the environment and human health. In forensic science, GC is used to analyze evidence and identify substances, helping investigators determine the cause of death and identify the presence of drugs or poisons. In the pharmaceutical industry, GC is used to analyze chemical compositions of drugs and ensure their purity, helping manufacturer ensure the quality and consistency of the product.
In conclusion, the GC-FID method calibrates using the principles of Beer's law, a proved to be robust and reliable technique for the quantitative analysis of ethanol in local alcoholic beverages. The linear relationship established between the detector response and ethanol concentration facilitates accurate determination of ethanol content in various samples. This method can be effectively used for quality control and regulatory compliance in alcoholic beverages industry. Future work may involve exploring the analysis of other volatile compounds in beverages using GC-FID, further extending the utility of this analytical approach. So that's the end of our video. Thank you for watching this, and I hope you get many information from this video.